podcast is brought to you by LMU Munich.
The title of my talk is, now it is Quantum Instability of the de Sitter space. Originally I thought I would call it The Red and the Black, but then I actually reread the novel and found it pretty boring, so I decided that more academic title will be appropriate. The motivation for the studies which I will describe today comes from the problem of the cosmological constant. The problem can be formulated in the following way, that one can say that the natural size of the cosmological constant is the Planck's length, natural to the -2. And in reality, you have to substitute the minimal distance in the universe, but by the maximal distance in the universe. And that is the question why it happens. It is clear that some infrared effects are important, but how to go from this UV cutoff to the IR cutoff. And to study this question, I actually will unite a number of systems. As some joke, I call it commutative diagram, not because I pretend to know algebraic geometry. I don't, and I don't care really, but because there is a fantastic unity between very different problems. The same mechanism is somewhere behind the scenes. To explain the diagram, the supercharged nuclei is in many respects analogous. To the case of black holes. On the other hand, it has analogies with the Schwinger processes in constant electric field. This is analogous to de Sitter space. Both are actually they have descriptions in non-unitary conformal field theory. There is an analogy with constant magnetic field, which corresponds to ADS and is described by the unitary conformal field theory. By the way, I have to say, I should have said it already, that there are hundreds and hundreds important and relevant papers on these subjects. And I will not give any citations because, well, it was rather difficult to incorporate it here, but in a few days I plan to post the paper on the web, and hopefully most of relevant references will be there. Now, I will start with, we will discuss, our goal is to discuss infrared phenomena in all these cases because of what I said in advance. These infrared phenomena can stabilize or destabilize various things. And there are several themes which I will be touching. The first one is the topic of renormalizability in non-equilibrium situations. The claim is, which I hope to demonstrate right now, that renormalization group breaks down. What do I mean by that? What we have to expect? In normal quantum electrodynamics, the physics at low energy does not depend on the way you complete the theory in the ultraviolet. There is this separation of scale, and we call it renormalization, renormalizability. We will see in a moment that it's not the case in the non-equilibrium situation. I will start from the most standard setup, which appeared in literature many, many times. Let's consider, say, one-dimensional fermions, so it should be, it should be B, actually, it's a charged field. Actually, I probably also had to warn you that I wrote this some time ago, so when you see that what I'm saying has the opposite meaning to what is written, stick to what I'm saying. Now, we have some external field, A of t. We have the modes. We have the modes which at minus infinity in time are single exponential, the Yost functions. There is Bogolyubov transformation of this mode, so this is absolutely standard setup. And you can see that the transition coefficient for homogeneous fields are independent of beta, and that the mode with kz, with particular kz, is produced when it crosses the horizon defined by this equation. And we can calculate the current. Again, it's fairly standard calculation, but the reason I'm doing it is to stress the following feature of the answer. Remember, we try to describe homogeneous electric field, constant electric fields. We have both space and time translation invariance in the system. So one would expect that if current is either zero or constant or something. That's not what happens. The current is proportional to time, so the symmetry of the problem gets broken. And I will interpret it in a moment. You see that the current turns out to be proportional. There is a certain factor, depending on the Bogolyubov transmission coefficient, is proportional not to field strength, but to vector potential. That would be no surprise. It's a typical situation with the axial anomaly if we had massless particles in the system. But this is a situation with massive particle. With massive particle, we have also, you can interpret it as an anomaly if you differentiate it in time. This will be anomalous divergence. Then we have the field strength on the right. But what is interesting is that, again, what is written is not, here should be exponentially a small factor coming from this guy. Okay, so that's the first lesson which we draw, that we break down the symmetry of the problem spontaneously. We have to set up electric field in the past was zero, then we turn it on when we wait, and the result is proportional to the total time since we turned on the electric field. And if you calculate the correlation function, you get a rather curious relation. Again, t is the total time like that. And you see that if you take this big T to infinity, you get a very strange singularity, which is exists at non-coinciding points. Moreover, if the ultraviolet cutoff is of the order of ET, then you see that the result of your calculation is 100% dependent on the way you choose the ultraviolet completion. Actually, this is this is not such a surprise, because imagine you have one-dimensional system. Imagine that you created two pairs on the right and on the left, and two components of the pair start flying towards each other. When they collide, their energy can exceed ultraviolet cutoff. And that's the mechanism responsible for this sensitivity to ultraviolet completion. At the same time, what's interesting is that if you calculate in-out matrix element, then nothing happens. You don't notice this non-generalizability. So let's keep this in mind and switch to the de Sitter space, where the situation is very similar. How long I'm talking? I didn't notice. 20 minutes. Okay, so I was talking for 10 minutes, and I described about 1/10 of what I intended to say. Okay. So once again, if de Sitter, I remind you that the de Sitter space is just the analytic continuation from a sphere. It has basically a hyperbolic version of the rotational symmetry. All this is well known and quite simple and nice. You see that if we don't break this de Sitter symmetry, then there's no hope to get big back reaction. Because, for example, if you take a square, if you take square of scalar field, or if you take the energy momentum tensor, it basically will be constant, will not depend on the position. That's because of the symmetry. So our only hope is the broken symmetry, and indeed it is there. So there are several different cases which we have to discuss. The first case is the case of the Poincaré patch. This is, in this case, this Poincaré patch describes the expanding universe. It has some fatal attraction to cosmologists. It started with the theory of permanent creation, or how it was called by Hoyle and Narlikar, and then it also used in inflation. And it's indeed a very you can visualize what's going on very easily in this case. The problem is that it's not geodesically complete space, and I will return to this a little later. Now, there is a conformal diagram. The Poincaré patch is defined by this condition. And the first question you can ask, since we're interested in de Sitter symmetry, as I explained, it's very important to break down de Sitter symmetry, whether it would be broken down simply, naively by this condition, because it's not fully de Sitter invariant condition. The answer, which I will demonstrate, the question is not trivial. The answer depends on the vacuum you are using. For the case of the Bunch-Davis vacuum, again, a Bunch-Davis vacuum is just the green function which you inherit from the sphere. You have a unique green function on a sphere, and you make analytic continuation, and you have the green function called the Bunch-Davis green function, which has nice properties, which is some Legendre polynomial depending on the scalar product for free fields and so on. Since we are in non-equilibrium, we need various black and white green functions with pluses and minuses. And here I just wrote down. And you see, it's not completely trivial to check symmetry of the system. You have to consider these non-trivial transformations, symmetry transformation, which actually a priori they violate the de Sitter symmetry. But after some calculations, which I of course will not be describing, I just you come to the conclusion that if you have the Bunch-Davies vacuum, the analytic, because of analytic properties of the green functions, violation of de Sitter symmetry goes away. If you have any other vacuum, or any other you make small perturbation of the green function, then breakdown of de Sitter symmetry is 100%. So in this sense, the Bunch-Davies vacuum, which is also very much favored by people who work in this field, is a good thing. It's a natural thing which preserves, on a free level, it preserves de Sitter symmetry and so on. However, there is a simple calculation which you can make in the Poincaré patch, which shows that although the symmetry is unbroken, so all Feynman diagrams have this symmetry is unstable. Imagine that we vary a little bit the occupation numbers. Then the claim, after some simple calculation, you can claim that that there is linear instability, that there will be more and more creation of particles, and as a result, the symmetry will break down. It's not clear what will happen in the full nonlinear scenario, but at least linearly the symmetry is unstable, somewhat analogously to the specific heat of the negative specific heat of the black hole, but I will return to that. This is the situation in the Poincaré patch. There is one one question to be answered. The most common objection against instability in the de Sitter space is that because of if you have some perturbation, because of the expansion of the universe, it will be diluted and cannot lead to anything interesting. Well, that's in some senses true. Well, no, it's not really true in any sense, because you know, indeed when you have expansion of the universe, there is dilution, but it is compensated by the increase of co-moving modes. So you cannot trivially say that there is some exponential suppression or something like that. It's all subtle dynamics. You cannot avoid solving some kinetic problem before deciding whether the universe is stable or not. You cannot just. Okay, now let me give you one quick analogy of what happened to the situation like that. I will not be able to explain much details. Let's consider the hyperbolic motion of a charged particle. You have the golden rule for radiation of photons, and this is the vertex operator, this is the square of current, and you get the Wilson loop, but it's slightly unusual Wilson loop, very interesting one, by the way, non-equilibrium Wilson loop. You see you have I epsilon prescription in this Wilson loop, which is different. And you can easily calculate the emitted momentum, and you come to the conclusion this Wilson loop actually reduces to the local expression because of this symmetry This is Lorentz-Dirac equation, and it's well known that this equation, that the radiation is 0 for the strictly hyperbolic motion, and the hyperbolic motion is the solution of this equation. However, any small variation of this V would produce a runaway solution. And Dirac, by the way, tried to eliminate it. He noticed that things are good if you put both initial and final condition on the solution. This corresponds in our language to in-out matrix element. Indeed, this in-out, they don't experience any catastrophe, but physical matrix element do. There is runaway solution, and analogy which I want to convey to you is that just like here, when we have a Poincaré patch, okay, de Sitter symmetry, de Sitter symmetry is unbroken. Just like for the strictly hyperbolic motion, you don't have radiation. This thing is 0. Yeah, this thing is 0. But slightest variation leads to runaway solution. Okay. Why it's not working? Now I want to consider the interesting case from my point of view is the case of the global de Sitter space. In the case of the global de Sitter space, there is a theory, mathematical theorem, which tells us that it is classically stable. By that, it means that if you have you can set up a well-defined Cauchy problem, and this Cauchy problem is well posed in the sense that if you vary it a little bit, its variation of the whole trajectory will be small. So in a vulgar language of a theoretical physicist, it simply means that you have Schwinger-Keldysh tree diagrams. They solve the Cauchy problem. The solution of the Cauchy problem is Schwinger-Keldysh with tree diagrams. And that these tree diagrams don't diverge. They don't have infrared divergences. And that's indeed the case. You can see it immediately. Now what I'm going to do is to show that beyond tree diagrams there are divergences and the stability is lost. Okay, it's convenient to calculate the one-point function not in the full global space described by this conformal diagram, but by using what can be called anti-Poincaré patch. When time goes in the opposite direction to the standard Poincaré patch, and you see that the correlation function will be identically the same, as it's a precise statement based on causality of Schwinger-Keldysh diagram that calculations in anti-Poincaré patch are the same as in the global space, which may be a little strange because this anti-Poincaré patch seems to be contracting universe, while the global space is non-singular, but this is an exact statement. And you can calculate Feynman diagrams like that. There are simple Feynman rules or Schwinger-Keldysh rules. You actually attach an arrow of time to each particle. Time goes, as is well known, time goes from down to up. Is that right? Yeah. Some of them goes backward in time. Anyway, just believe me that you can do the calculation. And here I describe the calculations. the key point is that you get logarithmic divergence. So when you, it's the consequence of symmetry that, and it can be explained that these diagrams, there are two diagrams here, plus complex conjugate, and each diagram can be easily expressed in terms of the modes. It's a very simple calculation. And as a result, I have to go quickly here. As a result, you have two factors. You have, first of all, logarithmically divergent occupation number and logarithmically divergent Bogolyubov coefficient. So as a result, we end up with slowly changing alpha vacuum. And so you started with the normal Bunch-Davis vacuum, but then you get slowly changing alpha vacuum with the whole Fock space over it, because the occupation number is changing, and Bogolyubov coefficient is changing. That's a nice calculation. Okay. Nice calculation, and there is a challenge which the thing which I haven't done completely, I've done it to some extent, is to sum up the leading logarithms. There are, if you have a system with interaction, in the one loop order you have logarithms in the first power, in the second order it's logarithm in the second power, and so on. So you can ask what would happen if you solve the leading log, but I have some approaches to this, but the problem is I don't have the answer. Now, you can calculate various things and discover that indeed the de Sitter symmetry is broken, and we have that's the setup for summing logarithms and so on. You have the physical picture is that of the cascade, where momenta increase, and that's precisely the Kolmogorov cascade for turbulence. Except here it's very quantitative. You have very well defined Feynman diagrams and the problem of leading logs and so on. The leading logs are summed in principle by the Boltzmann equation, and there are several processes to be taken into account, but it's a complicated matter and it's not completely solved. I must say that kinetics is always a dangerous terrain. For example, kinetics of dialectics, which is somewhat similar to this equation. In this case, there have been it started with 3 fundamental but incorrect papers. One of the authors was Wolfgang Pauli, the second one was Rudolf Peierls, and then Isaac Pomeranchuk. It's very easy to make a mistake here. So that's why I'm saying there's no answer. I have an answer, but I don't want to tell it to you. Okay. Now let me describe in a few minutes another manifestation of instability. Imagine, Nati Zyberg today said that he gave as a guide for the perplexed, he said that if you are perplexed, go to flat space. Well, I sometimes stay perplexed in a flat space also, but still, let's try to go to the flat space. Namely, let's have the space for which the scale factor, the warp factor, is like that. So you have Minkowski space, then curved space, then Minkowski space once again. And you can solve things there using WKB. And you can find the green function at plus infinity in terms of Bogolyubov coefficient. Bogolyubov coefficients don't depend on momenta. That's because of de Sitter symmetry. And there are two pieces, and of course we start with a pure state. We must end up with a pure state. And the full propagator is the propagator of the pure state. But if you remove oscillating term by Koch-Graining, you get a precisely thermal propagator with a temperature which is a Gibbons-Hawking temperature. Now, the next step would be to see if we have, it's well known for a long time that there is a Jeans instability at finite temperature. Will the Gibbons-Hawking quanta be real? That's why I called it the case. If we find that there's no Jeans instability, but there is observers detect temperature, that would be the triumph of subjective idealism. That's why I call it this way. But this is not the case. So subjective idealism is out. When you calculate the polarization operator, you find that indeed Jeans instability is there. Okay, now I'm coming to the close. In the standard picture of inflation, we postulate that the cosmological constant is 0, and we have an inflaton, and we have the action like that, and we study it. Now, at the same time, it's not, this action, of course, has a very well-defined solution, namely Minkowski space with 0 scalar field. The question is, yeah, I see a triple exclamation here. Do you have 5 exclamation signs? No? Yeah, I should be finishing, indeed. I will be finishing. Actually, what I was trying to say, without much eloquence, is that in the global case, when you don't have the cosmological constant in inflation, you have to assume that somebody pumped up this system to some high excited state. What is unclear is who did it and why. When you go to the non-zero cosmological constant, then there is something like radiation damping. The system cannot be in a stationary. It must evolve. So my guess is that it might be useful for some models of inflation. Instead of introducing inflatons, just look at the cosmological constant. And because I believe the instability of this thing is now proved from the various angles. So there are many other things related to string theory description of this situation, which I'll skip. The only thing I think I will finish with saying that we certainly see that the cosmological constant cannot survive. It is a challenge, and it's a beautiful, beautiful field. There are still, I'm sure, there are hundreds of undiscovered facts about all these stabilities and instabilities. And this field will, I think, eventually lead to the explanation of why we don't observe, why the observed cosmological constant is of the order of the size of the universe to the -2. But it may take some time. It's not that it is around the corner. Thank you.
Any questions for Sasha?
I mean, dropping the scalar field, if we just start with the Einstein's action plus the cosmological constant, it doesn't seem self-consistent for the curvature to deplete, because there isn't a solution without curvature.
Sorry, I don't hear it very well. So
It's not clear to me that the proposal is self-consistent. I think you're claiming that in general, de Sitter space spontaneously decays to flat space. But I can
no,
write...
no, I'm not saying that it's a flat space. I'm saying that when you, the thing I know is that if you have a cosmological constant, then the system is unstable. What is the result of instability? I don't know. I hope it might be the flat space, but that remains to be shown. So I'm not claiming I proved this. I proved what I'm claiming to prove is that the system is unstable.